Okay. Okay, so, today is, I have to turn off my speaker. Yeah, I don't need to hear myself. No, stop something. All right. So I think what we're going to do, because we're getting really near the end of the quarter here, first I need to make sure, is anybody graduating this quarter? Right? So y'all's stuff is going to have to be done a little bit early, or at least that last day of class. I have to make sure that you're all graded and submitted. So y'all, anybody who's graduating needs to send me an email with ENGR 592 in the header that says, I'm graduating, right? And so I need to make sure that I take care of that, right? What we're going to do is, instead of, it looks like we're probably really only going to have one more assignment due, and then the final, the last day of class is February 27th. Is that correct? Mm-hmm. Right. So the most we can do is get in one more assignment, and that's going to be based on what we're doing today. I'll let you use it over the weekend. And then the 27th will be an ODE solver. So we're not going to cover all the material that I really wanted to cover, but this will be good. So I'll take this chance to review even some of the ideas. Even though we're not covering all the material I wanted to cover, hopefully what we're learning, and we'll really try to drive that home today, is that we're learning how to do computational methods from an algorithm to implementing it to evaluating if it's really working. So presumably, if you're given any new algorithm, you can go through this. So whether or not we've gone to all the advanced algorithms we really want to cover, what you're really supposed to be getting a feel for is, how do you know something is working or not? And I think today, I'm going to try to drive that home. So on the report, yeah, it's going to be short notice. The report over the weekend, we're going to leave off the introduction and a lot of the math maybe, and focus more on really just trying to get the numbers out and think about the analysis. Because in reading the reports, this is the one thing I feel that we're still falling short of, right? You're getting all the other parts together, but you're still not critically analyzing the results you're getting the way I want you to see things. So again, that's going to be really the total focus of what we're trying to do today. Fortunately, it's an easy topic. Differentiation and integration. Well, I say easy, and I just lost everything. That was my... Right, so the idea is fairly easy. So I'll post the assignment later today and reduce the requirements on what we're supposed to do. All right, but let's just review. Oh, it's cutting things. Let's see. Take care of that. That. Y'all seeing the, somebody pull up when we see what you're doing? All right. Yeah, I'm just going to keep watching over your shoulders. You've got to stay on task. Okay. So we all know integration, right? It's just the area under the curve. And at a very high level, what we're going to be doing is taking a bunch of data points instead of a curve, dots on that curve, and it becomes a single number, right? That's fundamentally what when you do with integration. You have a curve, and if there's points on that curve, it's going to be reduced to a single number. And if you go back to your old calculus book, they talk about the Riemann sums, that sort of thing. And you can put these little triangles on it and do a left approximation, a right approximation. Like what you're doing is dividing up your curve into delta x regions, making little square blocks for each of those, right? So when you get those blocks, overestimate, underestimate, and that. So that's the general idea that we're trying to bring to mind. I was hoping to use exotic pictures. That's not going to happen, right? There's another thing to keep in mind. If you know a polynomial and you integrate it, you can algebrate it very quickly write down what the answer looks like. You can play that game on the computer too. So the integral of x to the power n over some region a to b is x to the power n plus 1 divided by n plus 1, evaluate it at b and a. So all you got to do is take b, raise it to the power n plus 1, take a, raise it to the power n plus 1, divide them, and then divide by n plus 1, and that would be an algebraic way to do it. So if you know those coefficients, you can play that game even on a computer. Didn't we just cover that thing on polynomial fitting? So in theory, when you do a polynomial fit, you get the coefficients of a polynomial. So if you were told then integrate that polynomial, you would know the mechanisms for what exactly to do to come up with the answer, right? So we're not really going to take much of that approach. We're going to focus more on this left approx, right approx, and center today. Differentiation, very different than integration. You take a curve, and at every point on that curve, you get new information, right? So if you take an approximate value of sine and say, I'm going to give you 10 points, and now I use that to integrate it, you get one number as your output. When you do differentiation on sine, and I give you 10 points, if you did it exactly perfectly right, you would get a cosine value at each one of those points where you're now evaluating, right? So the data that goes in and the data that comes out from an integration and differentiation, just from a purely data point of view, very different things. So that means that our interface to it is going to look a little different, and the numbers we expect to get out. For integration, we get back one real number. For differentiation, we get back a whole stream of numbers that represents the new curve. Got it? So differentiation, remember, is just the slope of the tangent line, a velocity, a rate of change, you name it, right? But a curve becomes another series of data, very different than a curve becomes a single number, right? And if we remember from our freshman calculus, it's just the limit x plus delta x minus f of x over delta x, and let delta x go to 0. We could do it plus delta x, or we could do it minus delta x. That would be forward, or we could do it backwards, right? So put that x, this would be x minus delta x. Or we can split the difference and do x plus delta x over 2 and x minus delta x over 2, and that would be centered about your spot, right? But then if you remember our calculus, it makes a big difference sometimes whether you're coming from the left or the right as to how this is going to work. So it's very easy to implement this in this numerical integration on the computer. Really, the trapezoid rule is what we're going to use. Higher order method are these Newton cotes. General idea is quadrature. So the ones we're going to look at today are just 1/3, 3/8, and the general Newton cotes. There's a full A method. So let's just jump in and get started. So you can go to the Wolfram site. Let's remember mathematically, the integral from some initial to final can be broken up into the integral of a bunch of little subspaces, right? So we go, instead of all the way from the beginning to the end, we go from x1 to x2, x2 to x3, x3 to x4. So if we write down all those little bitty integrals, then we just add up all of those. And so what we're doing is we're approximating all those little itty bitty integrals with areas. So here's the area. It's the height, which is f of x, times the width, which is delta x, right? So the height, and what's the height? It's not just f of x, it's the average of the two endpoints, right? So what's the average if you got two endpoints, n plus 1 and n? You go find the value at n plus 1, find the value at n, add them up, divide by 2, and that's your average because you've only got 2 points, right? So it's really just the average height for this trapezoidal rule. Average height using the two endpoints times the width of the interval, right? And it turns out the local error, and we'll talk about it in a little bit, is h cubed, right? It's h cubed times the second derivative at some spot in the middle of that interval, and we don't know what that spot is ahead of time. right? But there's something very critical to note here. If the second derivative is 0, what's it tell us about our error? Second derivative is 0 everywhere, then the error is 0, right? So this method is going to be exact, meaning no error, if the second derivative is 0. What does that mean? It works perfectly for lines. Why does it work for lines? Because we're taking, as our little interval, we got that, a line is just going to draw on the trapezoid, the top part is going to be a triangle instead of a square. And so we take the 2 endpoints and we take half the distance. And so that's exactly the area of that little triangle is 1/2 based on type. So we're getting that triangle exactly right if it's really a triangle. But if the line squiggles and curves at all, then we're only going to be on approximate, right? So the trapezoid rule, if we're plugging a line, we get exactly the right answer. But we're adding up a whole bunch of these little intervals, right? So if we added up n of those little intervals, then we'd have n times h cubed. And that would be our error. But note that n, the number of intervals, is inversely proportional to the width of those intervals. So really, n times h cubed looks more like h squared. So what we say is that this method is globally of order h squared. So if we don't have something that's really a line, then we're going to have a second derivative that comes turned on. We don't know exactly how much, but h squared, the width, is going to be what determines your accuracy. So we take that sine function and we approximate it with delta h of 0.1, we expect the error to be 0.1 squared. If we approximate it with 0.01, we expect the error to be 0.01 squared. If we got that up, right? And so if we do 0.001, we would have 0.001 squared. So what you can do, and we're going to do this as it's one of our games, we're going to start with the sine function, divide it up into 2 intervals, 4 intervals, 8 intervals, 16 intervals, 32, 64 points, and calculate the value of the integral at different values of the points. And what you should see is that as you add more and more points, you get closer and closer to the real answer as the value of h squared. So that's the game we're going to play today, right? But let's introduce all the other methods we're going to try today. There's a thing called Simpson's rule 1/3, Simpson's rule 3/8, and this Bole's rule. But what they're doing is exactly the same game as we're doing here, where you look at all these little intervals and you come up with an approximation for the interval. So they do it different ways. And really what they're doing is they're going back and fitting a Lagrange polynomial to that interval, and they're doing the integration over that interval, and this is what it looks like. From a computational point of view, all we have to do is know that Simpson's 1/3 rule, if it's constant spacing for all the x's, it's just 1/3 of the spacing times f1 plus 4f2 plus f3. Compare that to 1/2 f1 plus f2 is what we really had in this particular spot, right? So instead we're going to do, this is the rule we would do, and we would do that for each successive 3 pairs. But what that means is, well, we'll get to that in a second, right? So if we map this out, we would have f1 plus 4f2 plus 4f3. If we go to the next interval over, then we would have f4 plus 4f5 plus 1f6, right? So you take the next triplet and do 1, 4, 1, and the next triplet, and the next. And so what you want to do is just figure out what the coefficients are by rearranging that whole summation, and then you get the final answer. This one is globally of order h to the 4th, so it's higher accuracy than our simple trapezoid, which was h squared. So if we use the trapezoid rule, we should see one set of behaviors. It's going as h squared. If we use Simpson's rule, we get an h4th, and so we should see a much faster convergence to the real answer as we add more and more points. If we use Simpson's 3/8 rule, it's using 4 points for what they would call its stencil, right? And the pattern you use is 3/8 times the delta x plus 1, 3, 3, 1, right? Notice that this is an even number of points. This is an odd number of points. So if you were given 10 points, 2 points, 20 points, however many points you have chooses kind of which method you're going to use, the Simpson's 3rd rule or the Simpson's 3/8 rule. And then because this is for an even number of points, it's for an odd number of points, if that's the list of data you're given. Am I making sense? All right, so if you're given 10 points for your function, or 11 points for your approximate for your function, you would use the Simpsons rule to map out that, or the 1/3 and 3/8. So we'll talk about that in a second. The other then is this Lay's rule, where it's even using more points. So they're using 5 points when they're coming up with the approximate to the integral, and it gives you a higher order global error. So what we want to do is implement each one of these and see what they look like. So let's go and look at some of the nuts and bolts from Math World and see in general what these Newton Cotes things are all about. All right? So really, again, this is your curve. You're either fitting a line to it, and that's your trapezoid rule, right? And so even if we go through all of this, we end up with the trapezoid. Well, simply in here as just the, well, here it is, the 2-point is trapezoid, right? So really, if you follow through this analysis of really what you're looking at for the interpolating polynomial, what they're doing is integrating the interpolating polynomial for different numbers of x's. So if we really follow through that whole Lagrange analysis, this is what we get, and you can do it. So this is F1 and F2. This is the trapezoid rule, and it says right there that it's 112 h cubed times the second derivative. So that's the error we were reporting. The second derivative is 0. There is no error, right? Because there's nothing here to add on to it, right? If you start looking at a 3-point Simpsons rule, you go through the whole Lagrange analysis. This is the final expression that you get, which simplifies to this statement here. There's your 1, 4, 1 are the coefficients, and it pops out that it's the fourth derivative that's going to be governing the error. So if your fourth derivative is 0, meaning your polynomial is of order 4, then you get exactly the right answer from this Simpsons method, right? So the Simpsons third 3/8 rule, they're using 4 points to calculate it. It ends up being the same order, but again, the idea that you're using an even number of terms versus an odd number of terms. And you can keep playing this game to any order you want. 11-point rule, higher point rule. We're not going to play that game. What we want to focus on is demonstrating that we know that a polynomial of a certain order is going to give us a 0 answer, and that if we use something that doesn't have a 0 error, that we have real control over it. By changing the discretization, we'll see that it converges at the rates we want. Hopefully that's making some sense. So the trick will be implementing this, this, and this in MATLAB, as long with this. So I've given you a function that implements that, right? How do we do these others? It's going to be a little trickier, but this is all you have to do. So in MATLAB, trapezoid is fairly easy. It's just 1/2 x plus and x times h. That's the height, the average height, times the width. Well, we can do this with one line in MATLAB, right? You take the y value 1 plus, add it to the y value at the 1 we're currently at. You see the 1 and the 2 plus. And notice, you can't go all the way, that one can go to the end. It started 1 up from the left end, and it runs all the way to the end. This one starts all the way at the left end, and it stops 1 short, right? So what we're doing is we're shifting the 2 lists of y, adding them together, and just multiplying by h. Does that make sense? So if you have a string of numbers, 1, 2, 3, 4, 5, and those are the y values associated with it, this whole trapezoid expression is taking the higher ones, the ones associated with 2, 3, 4, 5, adding them with the ones associated at 1, 2, 3, 4, taking half of that and multiplying by h. So I believe this sum should do it exactly, right? It's a little trickier for the other ones. And it's also trickier if we don't have constant spacing. If we don't have constant spacing, if it's not really 0.1, 0.1, 0.1, we have to multiply by the right delta h at each interval. So we can do that, and that shouldn't be a divide, it should be dot star. I was thinking about differentiation and integration, right? So it's the same thing, except we have to take the right value of the interval for every x, which is going to look exactly like the differences of the lines. Okay? So we'll play with that code in a bit. or maybe even right now, if it looks good. Sorry, I'll get this. Is it making some sense here? I know I'm blazing through it. What I want to do is start seeing and getting into this code and figuring out how we're acting. Right? So here is my integration one. So I'm just going to go from 0 to 5, break it up to 10 values of 10. The number of intervals, that means the delta x is h max minus h min, right? So I make my list of x's. So here's my list of x, so I'm going to enter the max. I'm going to just do a sine value. So if I go from 0 to 5 of sine, what's the integral of that? Integral of sine over 1/3. Sine goes up, sine goes down. Positive area, negative area. Full area is
balanced.
what? 0. Right? Not 7. 7. Okay. So MATLAB solution, you just throw out a trap Z, you can do X values, Y values, and come up with the answer. Let's see if I run this, what I get. Right? So MATLAB said, yep, 10 to the minus 17. My solution was 10 to the minus 17 as well. Wait, I've got 3 different solutions. Well, that's because I call my trap the Zoid method, the substance 1/3, the substance 3/8. Be very careful. If you open up substance 3/8, it actually is just a trapezoid method to give you the exact same answer. The thing we're going to do in class in a little bit is modify this so that it actually calculates the proper trapezoid. But the trapezoid one, as I had said, is 1/2 the sum of these times the different in x. We can go, and instead of just doing zeros, let's plug in something that has a non-zero value. So what's the value of sine squared from 0 to 5 if you integrate that? That's what we're going to be integrating here. Is it pi, pi over 2, 7, or 8? Integral of sine squared. One hump, that would be a little positive. So it's got to be a positive number because it's squared, right? The answer, I believe, is 5. Or at least that's what MATLAB tells me, 3.16. And my solution is 3.146. So it looks like I'm getting good answers. But am I really? Assuming you trust MATLAB. It's analytic, so we can either let MATLAB calculate it numerically, right, which is not being done analytically, or if we really know it was pi, we could do pi minus MATLAB solution. We could do pi minus my solution and see what we get. Right? The answer is really pi, so the answer is 10. The head calculate about 10. Right, negative infinity. Well, so it's 0, 0 says on the money. This might be a little harder to do than we thought. So let's instead of intervals, take 3 intervals. We'll see that. Oh, yeah, and we actually even get the complex number here. It's way up. So something's wrong somewhere in our code with our values. You can just take 3 intervals, 5 intervals, goes to negative. Right? So there's a bug in our code. We shouldn't get a value like that. 3, 4, and so it might be hard with this to get any meaningful numbers out of it. It's really only giving us these. So, all right. So the goal we're going to have to do is to implement the Simpsons rule. Instead of it being the trapezoid rule, we have to change this to the Simpsons rule, right? So let's go back and look at what the Simpsons rule said. Simpsons rule said that what you want for each interval is 1 plus 4 times the next one plus 1 times the next one. And so you do this just scooching over and over and over for each of the intervals. That would be the interval for this first interval. Then you move over to the next one. So we go from here to here. We would move to n plus 1 and go over. And so we would go to the next set of points at 1, 2, 3. The next one over would be 4, 5, 6, 7, 8, 9. If we look at the coefficients, that's going to be the trick, and I'll let y'all sit and figure that out. You could play the same game as we did in the MATLAB for the trapezoid rule. But we need to know exactly what the shifts are, right? The difference between, it was 3 values that you had to add. So we end up with 3 separate ones. Remember, we could have done this sum. It's just this plus that. So we could have added up 1 times the very first one, 2 times all the intermediate ones. We should. Is this not going to be the same thing? We're going to take y1 plus yn plus 1/2, nope, instead of a half, 1/2 times the sum of 2 y2 to the n minus 1. Shouldn't that be the same thing? When we take hopefully y'all are able to follow along and see what I'm doing, right? So here I took the sum of every element, and since that's a sum of sums, I can rearrange that sum any way I want. So I got, out of this thing, I only got the very first element plus y1. But I got y2, I got it here, and I got it here. So y2 I got twice, y3 I got twice, all the way up to the very last one. I only got the very last element once. This one never contributed the last element. So if I just start at the very one from each end and take that twice and pick up the very first and the very last element, then I've done the same thing. You see how I've shuffled the numbers? So wait, I'm multiplying a half and multiplying by 2. Can't I just take and do all of those? A half times 2, right? Now, I'm still dividing by this, but what do I do over here? This y1 and y2, we're still supposed to be divided by this. So we run into a problem here. I don't know what the very first beginning and end h were. This really should have been divided by x. The very first one is 2 x1 is what I'm dividing by here. Right? The very last one is divided by x on the n minus x on the n minus 1. That's the delta x to the very end. Think that's going to work? I don't know. Let's take a whirl and see what happens. Oh, and I put it in the Simpsons rule. So Simpson should give me, since it's 1/3, it should still give me the exact same answer as the Trappist way. Where did I put Simpsons? Let's see. Integration line 14 on Simpsons. My solution. So it doesn't like something. I've got to miss the bracket. Do I know what the bracket I'm using? That one is there. That one goes there. 5, 2 minus 5. I don't want this sum of that one. This gets divided by x 2 minus that. Save that. Run it. Matrix dimensions must agree. Oh, different problem. So what did I do about my matrix dimensions? I'm taking two and one I can do. And in minus one, I think I can do. It's going to be wrong, but tell me maybe it's working. Okay. So my problem is in this part of it doesn't like my matrix dimensions. 2 and then this is short by 2, and this is short by 1. Right, I stopped off one in the front, one in the back, so I think I need to start here. Yep. All right, so it is now giving me what appears to be the right answer, right? So what I've done, let's compare. This is the way I calculated the first time, right? And what I did is I shifted the two sections of the array and added them together on the fly. Here, so that was the Wi-Fi.
Yes. I'm reconnecting right now to Wi-Fi.
But I'm connected to the real network. So I'm still recording. Yeah, and I lost my Wi-Fi too. All right. Well, been good. Go ahead and take and see what are those coefficients. So tell me, you need to work through the Simpsons rule and modify that. Simpsons rule to properly work. One is not the third. What the integration should be? Fix that routine and run it, and see that you can get 3.14. So let's do that now, and then I'll start talking about the
Just got the amount of code pulled out. What would you like to see again?
So what you're supposed to be working on right now is the Simpsons 1/3. So trying to set that up properly efficient. So 1, 4, 1 to make that. So you're talking about the code that I just typed? So why is it, where did the 1/2 go? So the first time, so this is why I thought what I just did is cover. The first time I had it is you always took the average of the parts, right? 1/2 of A and B of F1 and F2. 1/2 of F2 and F3. 1/2 of F4 and F5. 1/2, remember.
Half like that and half like that.
Yeah, I really should like to. Okay, so what's happening? One half of 1 and F2. That is I1, right? That's the left and right hand side of I1. We would do 1/2 of I2, go from 2 to 3, so you do 1/2 of it, right? We take for I3, we go 1/2 of F3 and F4. We can rearrange that sign. Note there's only 1/1 multiplied by half. Here we got half F2 and half F2, right? Here we have a half F3 and half F3. So anything on the middle, 2 and 3, get multiplied by the whole. Anything on the very end is a half, so that 4 at a half, right? So that should be wrong, right? So the very outer one's going to have a leash right? So in general, this then is the sum of all of the elements. They don't have a half. This is all multiplied by it. So this is that's the sum from 2 to n minus 1, right? And the reason it doesn't matter here, we're doing sign. What's the value of sign? So that's why I got back. So you just made a good point. When I factored out the very first to the very last, when I just showed y'all, I forgot to put the 1/2. I mean, I'm getting it again. But I was integrating the sine function. And the very first element of sine and the very last element of sine was a period. the F value rather than 0, right? So I'm adding zeros in this particular instance. I would have done cosine. It wasn't work, because cosine is not going to be 0 at the interface. So yeah, it looks like he's exactly right, because I needed my my 1/2 value in there. Right? So this is something you should be aware of when you're testing your codes, is that the sample problem you did may actually not trigger an error. Algorithmically, if I'm 0 at the input point, then I just know I will never ever pick up. But if my function is not 0 at the end point, I'm going to get the wrong answers. And that can be something that becomes very hard to find out unless you know the algorithm and you know your particular test case. Right? I said, oh, well, sometimes my function works, sometimes it doesn't. Why? Well, this is exactly the sort of critical analysis I want you to find a spot when you can do stuff. Cool, good. So what are the coefficients are supposed to be? So on the trapezoid rule, it was 1/2 for the very first one, 1/2 for the very last one, and then 1 for everything in between. What are the numbers we're going to use for the Simpsons rule? 1/3 rule. The very first one's going to get a coefficient, the very last one's going to get a coefficient, and then the ones in between are going to get different coefficients. Has anybody told us what that pattern is yet? You need to sit down and write that out before you try to implement Simpsons rule. I want you to be working on what those coefficients are. We can ask you to say. It should be in Chaplain's notes on the Simpsons. Exactly that we speak in person. Let's see if mine works. So my solution does not work with cosine. So
choose odd and even terms.
How do you choose?
Like we need to take even terms for those which are the copy.
I don't know. How do you do that? Is there a MATLAB trick to do that? So what are the coefficients? Let's start there. You said the even term, something like the odd term. So my system is integration.
We can give a step size of 2, like we can begin with 2 and give a step size of 2, but I don't know what is the last term.
So what does it look like for the very first interval on Simpsons 1/3? So it's F1 times F1 plus 4 times F2 plus 1 times F3, right? The next interval over is also 1, 4, 1, but which F's still in there, right? If it starts at F2, right? If it's F2, F3, and F4, then what you get is everything. Okay, it doesn't start. It's 1, F2, starts at F3, 4, F4, plus 1, F5, right? So what it turns out is you get 1 times F1, 4 times F2, plus you're going to get
2
times F3, and then what's going to happen when you shift over? Are all the others going to be 2, 2, 2, 2, 2?
4, 2, 4, 2.
Those are the spots, 1, 2, 4, 2, 4, 2. Okay. So then if it's 4, 2, 4, 2, 4, 2, you can call your math out as, you can put in the numbers 1 to the end, right? But can't you use 1 colon the space and then another colon? But you do 1, 2, 1 colon 2 colon n. And that picks up 2, 3.
Yeah.
That would pick up 1, 3. That would pick up all the items. So you start at 1. Right? Does that really work?
But what will be the last term, like if it's going by a step size of 2?
Then it will automatically stop short of where the end is. So it goes 1, 3, 5, and then we'll never get to the end, right? I mean, if you get to it, it'll stop exactly at the end of its even size, for 1 short. Okay? But then you have to know the size of that, because it's even or odd number. So what we really want to do is, if something's third rule, is check the size of the data you get at the very beginning to find out. Is it even or is it odd? If it's odd, then say, well, no, I'm not allowed to do that. Yeah, so right now I have an array called X that has 1, 2, 3, 4, 5 values. If I tell it X 1 colon 2 colon n, it picks up the first, the third, and the last value, because there's a 1, 3, and 5 on numbers. If I tell it skips 3, then it picks up the first, the third, and then it runs off the end, right? So it doesn't pick up the rest. So you can use the relay indexing to tell it, only pick up the easier ones. That would be 2 colon 2 colon n, and that's going to pick up every even term in it, because it starts at 2, 2, 4, 6, 8, 10, all the way to the end. If you do 1, 2, n, then it does 1, 3, 5, 7, picks up all the odd terms, right? So that's MATLAB shorthand notation for taking out those array numbers. Does that make sense? So if you have to do something to the even terms, you can do that. Something to the odd terms, you can play that game, so you already know the coefficients. Where you were just telling me is 4, 2, 4, 2, right? But the very first one is different, right? So you start at index 3 or index 2, not index 1. Do you get it? So with that in hand, I should be able to do the Simpsons rule also myself. So the pattern for Simpson is 1 for the first and last. The even ones get a 2 or a 4.
Even with 4.
Lesser multiplier is 2. Right. So it's 3/8. Whatever each was, we take the very first one, the very last one. Then we do plus a 4 for the even multiplier. Does it work like that?
Yeah.
Back again. Good. And we're live. Good. Thank you for telling me we're live. So this is what I was hoping to show you, is that, right? If here's my array X and it's got 5 values, you all see them now? Right? So there are the 5 values, so I just stop X. But if I do 1, 2, N, it picks out the first one, skips it 2, makes it the last. So if I start with 1, it only gives me 2 values because 1, 3, 5, 1, 1, 3, 5 should run up. Why did it run? Oh, I'm skipping through. So never mind. If I did instead 2. Right? If I do the even ones, then it does that. So what this means is my Simpsons rule, I should be able to do something that looks like this. Just said the even ones starting at 2, get a coefficient of 4.
Why are we writing 3 by 8 in the beginning? This 3 by 8 in the beginning. Is it like? It should
So all
be,
the even terms get multiplied by 4.
no, like 3 by 8 star H that you have written. It should be 1 by 3. With Simpson 1/3.
Yeah, so that's the coefficient that gets multiplied by everything, right? For 3/8. Right? So we can factor out the 3/8. We can factor out the H, right? The H being the width, the 2.
And it should be 1/3, not 3/8. For the 1/3.
Sorry, this is what it should be. So I'm in the wrong, okay, I'm in that, sorry. But is this right? So back up here, is the solid what I'm working on? Is it 4 times the sum of the even term? And 2 times the sum of the odd term? That's it. What doesn't it like up there?
The X value.
And I need one more. I haven't defined H yet, so what we're going to do is just make H the constant value of X2 minus X1, right? That's cheating because we don't really know that. Right? So this is not good code, but we have that. So let's hope that really is a Simpsons rule. Is that going to work? Simpsons 1/3. And we've got another pair to put in here. Index seems to make these dimensions. So where's my How's it? One, is it not like doing that? Okay, so what did I screw up on this one? So it does the swap. Oops, let me go back. So this will allow me to start at 3 and skip 3. It shouldn't bother. There. What's going on with this piece of code? Y'all can see what I'm doing here?
Mm-hmm.
I got, is that right? I can see this? So what went wrong?
Maybe after X we haven't put like the asterisk sign.
How many files am I sending? Number of values is 3. So I'm not even sending the big enough values as part of this game, right? So this is where I'm wrong. There was no check for number of values. So that's where I'm getting in trouble, is I set only 3 values to in the first place. And so this is running right off the end of the array. It's getting me in trouble. You'll see if I add some more values, the number of values I'm sending it. I'm still some trouble somewhere.
इसके बाद मल्टीप्लाई बंदा नहीं डाला ना तो वो करना है
इसके बाद मल्टीप्लाई क्यों क्यों चाहिए और तो हाँ इसके बाद वो तो ऑटोमेटिकली मल्टीप्लाई होगा ना
थोड़ी ऑटोमेटिक होता है मेरे को किसी और को थैंक यू बोलूँगी
This is Simpsons Y13. Yeah. So that's supposed to be, if I'm doing it right, that should be what is the 1/3, the coefficients for 1 or 1. So when you start shifting over, you get the odd term gets 1/4 to 1, then you shift it over 1/4 to 1. You shift that over. Correct. So I goes 1, 4, 2, 1, 4, 2, 4, 2, 4. So okay, between those. All we got to do is figure out how to do that. We could explicitly do a loop over the indices and multiply them. Add this together. But I'm trying to get this to work. So what am I doing?
I wish if you go to this and the array with the 1, 4, 2, 4.
You have a multiply application.
That is a programming error that probably might fix things. now it looks like, am I coming up with the right answer, or is that, is there a bug here, or is that the way it's supposed to work?
4 by 3.
That-
We should put 4 by 3 and 2 by 3.
Isn't this third,
Yeah.
No.
No,
That would be a 4 by 3.
mhm.
And I picked up the 8 as well. So I want to put that at 1/3 8 all the way to the beginning, so that I only have to multiply once, right? But am I getting into trouble with my numbers? Because we were just. I don't really get back to here. Is it 4/3 8?
Mhm.
And
Yes.
2/3 8? Is that what it's supposed to be? So is it a programming error or a logical error? Or is that really value you're supposed to get? Let's see, instead of 10 values, I go up to 20. I get a better answer, and I'm still off. But interestingly, I'm only off by a little bit, not catastrophic. So I suspect it's something with my end groups. I haven't been lots of years. Third. I'm supposed to take a third of each times one, a quarter of each times the other ones, and 2/3 each times each other. So it requires an odd, that's what. Need an odd number of terms. So this is a problem we will understand, right? This has to take an odd number of terms, it's not going to work. But this one now, you get a little bit of answer. And I, well, so I have to go to no. Really need to go over here. Is it about supposed to be 10? Is it supposed to be under E? That's what we part of our problem here as well. You gotta have the right number. We do it overtime and undertime. That's the only other question we have there. Right? So we're close. Right? But we're not terminating the sequence value of field to X line, right? So we either have to come up with the farthest one from the end, and it has to be the 2 from the end, right? I think this is probably where we're getting in trouble with this one. And really, some, does it go all the way to the end? The very last one is going to be, we might have to do one more, that should be stop one short, this should stop 2 short. Because we're
N-1.
well, choose 2. That is this. So we've got an indexing problem, but we're doing results, right? You don't have to track down what's going on with the code. What we should really do is put down in here a check that says, is the number of X and Y values even? And if it's not the right number, then what do we do? We either have to do something different to the very end of our instance rule, and say, well, resort to trapezoid rule from that last 4 pieces of this, right? Or we just say, can't use the Simpsons rule with 1/3 with an even number of terms. You have to use an odd number of terms because it's 3. I'm saying that right? I think, right? So it has to be, no, it has to be actually power. It has to be a power of 3, not just an odd. There's. When I have to sit and work all off by hand, I'm not going to
Divided is times 2 minus 1 minus 4. For all of them.
just what?
They equals like 2 minus 1 for all.
Where? For a simple 1/3 of code number that? Yeah, so if this one we set up for our constant space and page. Right? So when I set that up, I did two just color graphs. So that's another thing in this code is that it assumes that it was a constant space. There's no check in here. It said, are my delta X values really the same? Right? This is just taking the Simpsons 1/3. It's taking a list of X. Maybe it should really do a checking value of delta X. That's the values. Right? So there's something wrong with it, but we're kind of close. So I'll leave it at that. And that's the rest of the homework we all figure it out. Right? So this third create tool is really just implementing the options the way we do it right now. So yeah, we've got to work with that. Again, what we want to do is make sure that we're doing this all correct. So we're apparently not. And the question is, we're starting by 1, 4, and 3. Right? It's going to leave us with the very first element and the very last element. But this 1, 4, 1 template is moving across. We have to then make sure that we line it up with that. So it's really coming in blocks of 3. So it's not that I just need odd. I believe I need something that's divisible by 3 in order to use Simpsons rule, right? So write this out explicitly in terms of the F1 board, 1, 2, 3, 4, 5, 6, 7, 8, 9, and see really what it looks like in turn. Can I do it for 10? Can I do it for 11? Should we get that? So do 3 rules explicitly and see exactly where your indices have to stop. Because that's the problem we're having with that. If you have a little bit more time in class, I want to instead of just the integration, I want to go over and look at the differentiation. Well, so here's actually the right. So there are answers right here. Right? We stop at n-1 for the odd terms, stop at n-2 for the even terms. You start right. So there's the answer is that these both stop, even one stop before you get to the end, the odd one stop also before you get to the end. It's only the very 2 outer ones that do it. So that's 4 goes with the odd terms. Is that right? 4 goes with the odd terms. And I put 4 with the even terms. You all caught that? Okay. Maybe that works a little better. But I'm still probably running 1 off. I think I'm going to have to do something like that. We should get a better answer, but we're not. So again, you have to go and explicitly write down what's going on. So you can either try to play a game of letting MATLAB sum and do the array things, or you can explicitly write up these loops. It might be easier in this case to just explicitly write the loop. But there's going to be some overhead for MATLAB, right? The reason I want to use MATLAB sum command is because that command is going to be optimized to just go and splash through the data at whatever stencil length you want. If you write out that explicit for loop, I guarantee you it's going to take longer to run because it's going to have to set up the loop. It's going to have to go count, pull up the individual elements. But MATLAB is going to be smart enough if you tell it the sum and you give it the array indices to go ahead and optimize it. So that way, something you can show your homework is I explicitly made a loop, right? Let MATLAB do it. We're just one ran faster to do it. These are the MATLAB numbers that do essentially what we're doing. Travel rule. We did documentation on that. And again, I saw a couple of homeworks where they said MATLAB routine something, right? You can read the documentation and find out, this was on, for example, matrix solvers. You read the documentation on MATLAB's matrix solver. It will tell you exactly what routine it's using. And the suspicion is that its timing looks very similar to one of the, I think it was Gauss elimination. You can see, oh yeah, timing work out this. All right. So what I want to do in the last couple of minutes of this is look at the differentiation, right? So we're going to round out the lecture. This is going to go a little bit quicker maybe, right? It's a little easier to figure out. So the approximate formula for differentiation is just the limit, or the exact formula, is when delta x goes to 0. But we can do this as a forward difference. If we're given a bunch of y values, we take the and divide it by the x values, and that should give us the derivative. Remember, that's going to return a whole array of values, not just one single value. The error is going to be a order h, meaning the width of the distance. The closer you get to delta, the smaller the delta x, the better the approximation of the derivative. So we can do a forward difference, a backward difference, where we look at the one behind us. This I better not start at 1, right? I better start at 2 here, or you'll get into trouble, right? Okay, and this one ends 1 from the end, right? But it's going to run off with I plus 1. So the loop on the top here has to stop 1 short of the ending of that. These are both of order h. We can get an order h squared, meaning higher accuracy one. If what we do is the center difference, where you take 1 ahead and 1 behind, and you look at this. And so this is really 2h, is what we're talking about here, right? Where do these come from? So this is good to know. We're going to need to know stuff like this when we start looking next week at ODE. So let me zoom in. This is just taken right out of the book. And so this is the little trick they use to come up with these formulas. So it's really just the Taylor series approximation that you're using, right? So f of x plus 1 is f of xi, the derivative of xi, plus the second derivative plus the I. If you just stop with that part of the Taylor expansion and you rearrange it to see what the different derivative looks like, you would say, oh look, there's my forward difference approximation. And it tells me explicitly what the next term is that I'm ignoring. It's of order h, and then there's order higher order terms. So this, if I just drop that off all together, we can say there's some value here, this order h, that we're missing. So this is what we do for the first order finite difference, right? What we could do is now take that and use it to come up with the second derivative by substituting that forward difference into the second derivative. So we, instead of stopping right here, we can take that expression and write the first derivative in terms, the second derivative in terms of the first derivative.
You mean like a derivative of the derivative?
Right.
Okay.
So we use this to express the second derivative with this standard approximation, right? So what we're doing is taking that second derivative and replacing it with just values of f. And so what you end up with is a second derivative that is expressed only in terms of first order values, no derivatives of your function. So it's a 1 minus 2 and a 1 that you would be using. And what you see is that this one, when you plug it all in, ends up as a second derivative of its first order, right? So we get a first order approximation of the second derivative, right? The other way we could do is we could go back and take that and plug this now back into what's up above. You start adding and canceling terms, collecting all the terms, and we see now that if we can take and figure out the second derivative in terms of the actual values, we would be up at order h squared, and we would just have a bunch of values of that. So that's what we're building up to here. We have the first derivative with the whole series of nothing but function values all the way up to the second order. When we collect all the terms, this is what this symbol looks like. It's a -1, a 4, and a 3, and you use it for x, x plus 1, and x plus 2, right? So this is the first term, the next term, and the next. So now we can write the derivative at any given position xi using our current value, something from one step ahead, and something from 2 steps ahead to calculate the derivative, and that's going to be a higher order derivative. So this is the forward difference approximation of second order, right? You can play this game by taking the Taylor series of whatever order you want and continually substituting back the derivatives, and you build up the pattern for all these coefficients. This is a little bit of a game, again, we'll play next year. But that's the general mechanism how it works. At the end of the day, what you get are the defined methods, and this is just taken straight out of the chapter's book. For all the different sort of methods. So the first derivative, forward difference, I can get it to order h or order h squared, or I can keep playing the game and get it to order h to the 4th, or h to the 6th. And so I have to use more and more terms in here as I build it up, right? I can calculate the second derivative, keeping one order or a higher order, a third derivative, and I can push those to whatever order I want. So we're going to be using some of these methods actually when we start solving ordinary difference equations. But what we're going to do for now is just look at the first order derivative and use either order h or order h squared. So the order h is very easy. The order h squared, we just use a slightly different template. And this is substituting in forward values. Well, substituting in backward values instead of x plus 1, what do you think is going to happen? We go x minus 1, and instead of it being, 3, 4, 1, it's 1, 3. It's in the other order, okay? So if we look at 2, 1, 1, it's called -1, 4, 3. It should be 1, 4, 3 in the other order because we're just doing it from the other direction. We can play the game also with the center difference when we would bring it out, and we expect the coefficients here to be different than either the forward or the backwards. But we're playing the game again of the interval we take 1.9, we take 2 times the difference. So look how the order of approximation goes up a bit higher. It was h and h squared. When you use the center difference, you get h squared and h to the 4th. So what we want to do is implement these different forward, backwards, and center difference, given the x and y values, and either calling it order 1 or order 2. Right, so order 1 or order 2, here it would be order 2 or order 4 would be the acceptable values for the center difference. And we're going to test it on a polynomial, right? So remember, for a polynomial, we know what the next order term is that we would be forgetting. It's f double prime in this first order approximation. It's a second order polynomial with f double prime is 0. So if it's just a line and we take first difference, we get the exact answer, right? If it's a anything else, we're not going to get it. And so it's trivial code to do this, where you just get the values and you spit it out. So what we're going to do then is play the game we did before, where instead of sending it 2 points, we send it 2, 4, 8, 16, keep ramping up the number of points. And we can see that the error in our derivative is less and less and less by a factor of h. So if we go from here to here, that decreased by power of 2, by power of 2, by power of 2. If it's h squared, our error should be better by power of 2 squared, 1/2 squared, 1/2 to the 4th, 1/2, et cetera, et cetera. So each time, it's ordered each square, we get 1/2 squared each time, right? The question is exactly then how do you measure it? Well, this is what we're going to do. We're going to use a function where we know what the derivative is. So plug in cosine, and you know the derivative of sine. So you can take the function value, you know what it's supposed to be, and the approximate value, just subtract those and see that the error goes, right? So, as it should. So you do one of two things, right? You're going to have not just one value for the error, you're going to have the entire way all the way across. So you can ask, is the error uniform? Will I always make the exact same mistake? If I plug in sine and cosine, you're going to end up, yes, right? It's smoothly, I think, going to vary its mistake. But if you plug in some other function, you would see on some intervals the error is large, and some errors the interval is small. And that goes right back to the idea that the error is actually related to some of the value of the second derivative. So if the second derivative is high, you're going to be making a large mistake. If the second derivative is low, you're going to be making a small mistake, right? And so even actually now that I look at that, the sine function of the second derivative is curved up, it's curved down with an inflection point, where the inflection points go to 0 in your sine, right? Or where the inflection points are. The second derivative is 0, and so you should get an exact answer in your inflection point. So you should see even in your error varies over the width of the interval, right? So earlier in the class, I put up a first order difference where I even showed you what sine looks like. And what you saw was the high. So when you first plot the difference equation with low resolution, the cosine point, if you take sine, you're supposed to get cosine. It's a little out of phase. But the more and more points you use, it starts to line up. And that's really because you're doing a forward difference and you're looking ahead. So all your derivative values are a little bit ahead or behind what they actually should be. So you see it looks like the whole curve starts shifting when you go. So those are the sorts of things we want to look at. The goal again is two-part. We want to look at numerical integration and implement the trapezoid, substance 1/3, substance 3/8, and this relay method. Test them. And when I say test them, that means plug in the function, calculate the integral. You should already know the integral of the function you're doing. And then just plot the difference between what these methods gave and what what you know it's supposed to. So you do it with where I gave it 2 points, 10 points, 20 points, 100 points, and you'll see that the error gets better and better and better. But how fast does it get better? Some of them will go linear, some of them will go h, some of them goes h squared, some of them goes h cubed. And so you'll see very different conversion rates on out of this. And so this is really all I'm going to see on the homework is you're going to have the code, you're going to have a statement of what integral you're trying to solve, and then just show a plot of the error, right? What the actual integral is and what the trapezoid symptoms relate to. Stick that all in one plot, right? So just have multiple lines showing you what the value of the integral is. They should all tend to converge fairly quickly to the value for a simple. We'll do the same thing with the derivatives, right? We're going to use forward, backward, and center difference. The difference here is you're going to have a function, and when you take its derivative, you also have a full plot. So it's not just a single error value or a single digit that you get multiple lines. So that was going to be a little tricky to figure out how to plot. Does that make sense? All right, so you might start with sine and set it to the forward difference with 10 points, and you see there's one line. Now you set it with 100 points. You see the line is shifted, whatever, and you should see that all these plots start moving and converging on what the side really looks like. But you can also quantify that by measuring the error with a root mean square type thing. So take the error at each point, figure out the max and error that you make at any point that would be in the one. So I'll post some codes that will help you out. again, the target's gonna be to show that we get the proper behavior. I wanna see really that y'all know how to spot that H squared and show that your code is working, right? So again, we're dealing with some fairly simple algorithms. But what we're really trying to demonstrate with this assignment is that knowing what the behavior of the code is supposed to be, H squared sort of error, that we know how to spot that when we run the algorithm, right? So that means, one, we implemented the algorithm correctly, and so if it doesn't do this, that means you just haven't implemented the algorithm correctly. So it's not enough just to get an approximate answer that says, oh, the integral is I squared over a period is pi. What we want to do is show explicitly, what we want to show explicitly, what we want to show is that our error that we make versus the number of terms we use in approximating that error behaves the way it's supposed to be. Right? So we have some mathematical criteria that tells us the behavior of the algorithm. But that doesn't excuse you from putting comments in your code. It's absolutely what you're doing. All right? When you look at your code, you really should put evidence of helpful equation here. Right? You should answer all the comment lines and say, oh, it's actually translating method in the place that's fine. It's supposed to be there. Right? You'll have like the assumptions 1 for 8, assumptions 3, and these just have a driving routine, drives and so forth. Put a giant loop. It's really what we're going to do for MLs to 100. That's right? And we just go over the different MLs, and then you can say, over here, not obviously we should look at say as a function of the MLs. And then the kind of guys who take the giant array and versus the spotlight. So I'm starting over here. Say that. That's the idea. Just put all of those. I'll try to post some code and have one that helps you along. But I'm going to see a very short statement in your homework that says, you know how to spot the error, right? You don't necessarily have to give the whole history of what the formula is for the substance third of all of these. You just want to say that this is what I'm integrating, and substance says this is the error I'm supposed to get, and show me that you can get that next one. And then your code will speak for itself. Makes sense? Right? So that saves you the burden of how to figure out how to write a bunch of stuff. And all you have to do is get the code code. So on a good day, I will give you, by the end of the day, I hope to give you a working substance third. Maybe. You have to come up with your own green 8s, your own blue based on that. And the forward depth, I think I've already done.